In this session, we will solve the problems of reaction engineering, mostly focusing on gate. So, you see, it is given that mechanism of a non-elementary reaction. So, this is a non-elementary reaction. The mechanism is described as A plus A, K1, K2, A star plus A, and A star giving R plus S. Now, we have to write the rate equation. So, you see minus RA equal to K1 CA square minus K2 CA star CA, right. So, that we have to finally formalize upon replacing this CA star. Now, minus of plus of RA star is equal to K1 CA square minus K2 CA star, CA star CA minus K3 CA star. And as A star is a highly reactive component, we will consider it as to be reactive intermediate, and we will set that rate of formation to be equal to 0. So, K1 CA square is equal to K2 CA plus K3 whole bracket CA star. So, CA star is equal to K1 CA square divided by K2 CA plus K3. So, if I replace it, so minus RA becomes K1 CA square minus K2 CA square CA divided by K2 CA plus K3. Right. So, K1 CA square, if I take common K2 CA plus K3. So, numerator is K2 CA plus K3 minus K2 CA. So, that cancels out. So, we have K1 K3 CA square divided by K3 plus K2 CA. So, that is the answer. Right. K1 K3 CA square, option C, as given in the problem statement. So, next, this is also a gate question. A liquid phase, let us write the information. A liquid phase reaction is to be carried out under isothermal condition. So, liquid phase isothermal reaction, the reaction rates as a function of conversion has been determined and is shown in the figure. What is that? Minus of RA versus XA, it is like this. This is 0.4, 0.7, 0.9, right. So, what choice of reactor combination? What choice of reactor combination will require minimum overall reactor volume if conversion of 0.9 is desired? So, XAF is 0.9. So, you see we have to convert this graph to 1 divided by minus RA versus XA plot. Right. So, this is starting from a maxima, here it will start from a minima, going to a minima, here it will go to a maxima, here it will drop to a minima, and again it will start increasing. This, then this, then this. This sort of curve is expected, right. Now, here we definitely must use a PFR. Here, as this decreasing 1 by minus RA is a decreasing monotonic function of XA, so it should be MFR. And again here we should use a PFR. So, our sequence desired PFR followed by MFR followed by PFR. Right. Next, consider the parallel decomposition of A following different orders. So, A giving R, RR equal to 1, giving S, RS equal to 2CA, giving T, RT equal to CA square. Determine the maximum concentration of the desired product if a PFR is used. If a PFR is used for CA0, desired product is R. So, we have to solve for CR max. PFR is used, CA0 equal to 2. Right. So, you see phi of RA is 1, or rather we can write RR divided by minus RA, which is RR divided by RR plus RS plus RT. Okay. So, 1 divided by 1 plus 2CA plus CA square, giving 1 divided by 1 plus CA whole square. Right. Now, phi is equal to dCr by minus dCA, 1 divided by 1 plus CA whole square. So, CR for PFR we have to integrate it. So, minus CA0 to CAF, we do not know what will be the CAF in order to maximize this concentration. So, this is minus of 1 divided by 1 plus CA, CA0 to CAF. So, 1 divided by 1 plus CA0 minus 1 divided by 1 plus CAF. Right. Now, CA0 is 2. Here. This will be the CR, correct? If I am correct here. To the power minus 1, no, no. I think it is plus, right? So, this minus 1/3. because minus 1 plus Ca to the power minus 2. So, 1 plus Ca to the power minus 1 divided by minus 1. So, minus 1 cancels out, there will be a plus sign. So, 1 plus CAF, right, and numerator is this. So, CAF is low, so definitely this term will predominate and overall this will be positive. So, now DCR, DCAF is 0, minus 1 divided by 1 plus CAF square minus 0. So, that we have to set equal to 0. Am I doing it correctly? Yeah. So, this we have to set equal to 0, because this is the derivative, or actually what you can do, CRF here, we can see that how CRF and CAF, how it varies, right, because it is monotonic function. So, CAF is 2 initially. So, 1 by 2 minus 1 by 3. So, this is 1 by 6 somewhere, and 1 by 2, sorry, initially it is 0, initially it is 0, and finally when CAF is 0, so it is 2/3. So, it will be like this, right. So, no, CA0, it is just the opposite. CA0 when 0, CAF equal to 2/3, CRF equal to 2/3, and CA0 is 3, so it is something like this. So, when CA0 is 0, then it will be equal to 2/3. So, that is basically the maximum CRF for CA0 or CAF equal to 0, right. So, CRF maximum, CRF or CR maximum is equal to 1 divided by 1 plus 0 minus 1/3, so that is 2/3. So, that is the maximum yield we can have. Okay. Number 3. At present, conversion is 2/3. So, XAF is 0.67. For our elementary second order, elementary liquid phase reaction, 2A giving 2R, right, when operating in an isothermal PFR. with a recycle ratio of unity R equal to 1. What will be the conversion if the recycle stream is shut off? So, if here we have a recycle ratio equal to 1, my reaction is 2A giving 2R. So, V by Fa naught R plus 1 R divided by R plus 1 XAF 2 XAF dXA by minus RA. Right, that is the formula for recycle reactor. So, V by Fa naught 2, then here R divided by R plus 1, 1 divided by R this C, R divided by R plus 1 XAF 1 divided by 2 into 2/3, so that is 1/3. So, 1/3 to 2/3 dXA K Ca naught square 1 minus XA whole square. So, we have this K Ca naught square V by Fa naught equal to 2.33 to 0.67 dXA by 1 minus XA whole square. Right. So, this is 1 divided by 1 minus XA 1/3 to 2/3 whatever. So, this will be point and this 1 divided by 1 minus 2/3 minus 1 divided by 1 minus 1/3. So, it is 1/3 3, this is 2/3 3 by 2. So, this is 3 by 2 multiplied by 2 is there, sorry, here 2, 2, 2. So, whole bracket 2, so it is 3. So, we have got this value. Next, it is V by Fa naught 0 to XAF that we have to determine dXA by minus RA. So, K Ca naught square into V by Fa naught equal to 1 divided by 1 minus XAF minus 1. So, that is equal to 3. So, 1 divided by 1 minus XAF is equal to 4. So, 1 minus XAF is equal to 0.25 and XAF is equal to 0.75. That is answer. Okay. Next 4. For a reaction A giving R, second order kinetics and Ca naught equal to 1 mole per liter, we get 50% conversion after T is equal to 1 hour in a batch reactor. Right. What is the conversion and concentration of A after 1 hour? Now, if Ca naught equal to 10 mole per liter, we have to find out the conversion. So, this is second order, A giving R, right. So, minus of dCA dt, which is Ca naught into dXA dt is equal to K into Ca square That is k into Ca naught square 1 divided by 1 minus Xa whole square. So, dxa dt dxa by 1 minus Xa whole square is equal to k Ca naught t, and here we have to integrate it from 0 to Xf. Right. So, we have 1 divided by 1 minus Xa f minus 1, so which is Xaf divided by 1 minus Xaf, that's equal to, a conversion is 0.5, so 0.5 divided by 0.5, that's equal to 1, which is k into Ca naught 1 mole, and T, which is 1 hour, right. So, K, let us write it in our inverse. So, K is equal to 1. So, that we have to get from the first information, and that simply we have to use in the second. So, here we have Xaf divided by 1 minus Xaf is equal to this K into Ca naught into T, and after 1 hour definitely. So, K is 1, Ca naught is 10, and this is 1, so this is 10. Right. So, Xaf is equal to 10 minus 10 Xaf. So, 11 by 10, 10 by 11 will be the answer. And concentration similarly we can find out. Let us solve some more problems on C. Let us see. Yeah, this one is good. The first order reaction, see, this is 5. This is a gate problem. For first order reaction, order 1, a first order reaction A to R. So, minus Ra equal to Kca, run in a experimental MFI. Find out the role played by the pore diffusion for the data given below. Ca naught equal to 2. Sorry, Ca naught equal to 100, not 2. And Ca naught equal to 100. Agitation rate was found to have no effect on conversion. So, it is not external film diffusion controlled. Right. So, under this situation, what is the data given? dP 4 pellet diameter 4 and 6, Fa naught 2 and 4, Xa 0.8 and 0.4. So, you have to reduce it to epsilon data. Right. So, you see when it is MFR, so we have V by Fa naught is equal to Xa by minus Ra effective, right. Minus Ra effective is equal to epsilon into minus Ra, and minus Ra is Kca. So, it is Xa divided by epsilon into K Ca naught 1 minus Xa, right. So, what we have? V K Ca naught, V K Ca naught, sorry, in a reverse way we can write. So, epsilon is equal to Xa by 1 minus Xa, Xa by 1 minus Xa into Fa naught by Ca naught, Fa naught by Ca naught, here V, and here we will have K. Sorry, K will be in the denominator. V is going to the denominator, V into K. So there are two data points given, right? So let's find out epsilon 2 by epsilon 1. So xa1 divided by 1 minus xa1 divided by xa2 by 1 minus xa2. Ca naught is fixed for two cases. So Fa naught 1 by Fa naught 2. V and K are remaining unchanged. So this is 0.4, 0.8, 0.8 by 0.2, and here 0.4, so 0.4 by 0.6 into 2 by 4. So this is for second case, it's 0.4, so it is 2 by 3, so it is half, right? So it is 3. Okay. Now you see epsilon 1 to epsilon 2 ratio, we have got 3. Now dp1 to dp2 ratio is 4 by 6, that is 2 by 3. So epsilon 1 by epsilon 2 is not equal to dp2 by dp1. So it is not a strong pore diffusion regime. Additionally, epsilon 1 by epsilon 2 is not equal to 1. So not a purely reaction controlling regime. So what we can conclude? Here it is an intermediate regime. Intermediate role of pore diffusion. So pore diffusion is playing an intermediate role here. So what are the options? Strong pore diffusion control, diffusion free, intermediate role played by pore diffusion, external mass transfer. So definitely external mass transfer, that specific option we have negated, because the agitation rate, which will influence agitation rate, means it will change U, right? So U has got no influence on this pore diffusion, on this overall rate. So obviously it is not at all an external film controlled system, and we have got this epsilon is not satisfying this proportionality with 1 by mt, that is a Thiele modulus, and mt is proportional to L proportional to dp, right? So dp1 by dp2 is not equal to, dp2 by dp1, I should say this is dp2 by dp1, 3 by 2. So this is not same, and additionally if it is reaction controlled, that both the epsilons will be equal to 1 and epsilon 1 by epsilon 2 must be equal to 1. So that's not also happening, right? So we can conclude that this is an intermediate role played by pore diffusion. Okay. Yeah. Okay. Let's see a different problem. A stepped input tracer is used to explore the flow pattern. So a step input pattern, this is question 6. A step input tracer test is used to explore the flow pattern of fluid through a vessel of total volume total volume is 1 meter cube and step input of tracer. Right. So, two curves are given. What are they? This one, this is C, 20 into 1 minus 1 by E, this is equal to 40, and that's time in second. And here we have curve 2, 12 into 1 minus 1 by E, that is 60, this is 20, that's in second. Identify for each curve in group 1 a suitable flow model from the list given in group 2. What is given? A, curve 1, B, curve 2, and here PFR and CSTR in series, CSTR with dead space 3, PFR and CSTR with dead space in series for CSTR. Okay. So, you see this is the C curve. So, F curve is Ct by C naught, right, and we know that dE dt or F curve is this, okay, fine, and this is equal to dE dt, where what is E? E is 1 by tau into e to the power minus t by tau, that we remember for CSTR only. So, E or F rather is dE dt, so 1 by tau e to the power minus t by tau, derivative minus of 1 by tau, right. F we have to integrate, 1 by tau 0 to t e to the power minus t by tau dt. Sorry, this is just I am writing the reverse, F E is dF dt, right. So, F is E dt. So, it is 1 by tau e to the power minus t by tau divided by minus of 1 by tau 0 to t. So, tau cancels out, it is 1 minus e to the power t by tau, right, that is F. So, Ct will be equal to C naught into 1 minus e to the power t by tau. Okay, fine. So, here this tau, okay, flow rate is also mentioned. So, V naught is 1 meter cube per hour, no, not per hour, per minute. So, tau is 1 minute, right. Now, here you see, if I set t equal to tau, I will get C naught into 1 minus 1 by E. So, that is equal to 40, right. Sorry, that is corresponding time, this is equal to Ct. So, obviously, we can understand that tau or this tau here for CSTR is 40 second, but what is the total space time? 1 minute. So, this is CSTR with dead time. a dead volume. That we have to conclude. Right. So, here we can understand that as we have no no response, no concentration is building up over this first 20 second. So, definitely this one is the PFR. Right. So, this one is the PFR. So, next is, so for PFR tau p equal to 20 second. Now, next here this gap you see it is 40 second. So, this must follow the same equation. If we shift the origin here, so this is 40 second. So, tau m is equal to again 40 second. So, overall tau m plus tau p 60 second. So, this second one is PFR and CSTR in series without any dead time. So, curve 1 is CSTR with dead volume, curve 2 is PFR and CSTR in series. So, that is my answer. So, okay. This is also GATE question 7. A liquid phase reversible reaction. Liquid phase reversible reaction, A reversible arrow B, is carried out in an isothermal CSTR. Isothermal CSTR. Right? Operating under steady state. Okay. Steady state. The inlet stream does not contain B and concentration of A, no B in the inlet. Concentration of A in the inlet stream is 10 mole per liter. Okay. The concentration of A at the reactor outlet for residence time, if it is 1 second, then concentration at the outlet is 8 mole per liter, and if we increase the residence time from 1 second to 5 second, concentration of A drops to 5 mole per liter. Right. Assume the forward and backward reaction are elementary following first order rate law. So, it is elementary. Right. First order. Also assume that the system has constant molar density. So, delta V is 0. Sorry, delta V is 0, no volume change. The rate of the forward reaction, right, in second inverse we have to calculate. So, you see minus RA equal to K into CA, K1 into CA minus K2 into CV. Right. So, this is K1 into CA naught into 1 minus XA minus K2 into here it will be CA naught into XA. Right. So, that is the reaction rate expressed in terms of fractional conversion. So, CA naught is 10. sorry, Ca naught no B, and Ca naught is 10. So 10 K1 1 minus Xa minus 10 K2 Xa. Fine. Now tau 1 1 second. So tau 1 by Ca naught equal to Xa1 divided by, or here tau 1 by 10 equal to 10 K1 1 minus Xa1 minus 10 K2 Xa1, one equation. So, and tau 1 is 1 second, right? Tau 1 is 1 second. So, and Xa1, you know, we can calculate. 8 is equal to 10 into 1 minus Xa1. So, Xa1 we can calculate. And similarly 5, 5 divided by 10, Ca naught is 10, Xa2 by 10 K1 1 minus Xa2 minus 10 K2 Xa2. And here we have 5 is equal to 10 1 minus Xa2. So, Xa2 we can also get. So, from these two equations, I will get two simultaneous equations of K1 and K2. So, we have to solve for K1. So, that is the answer. Yeah. Okay. Let us answer this linked question 8 and 9. The liquid flowing through a reactor at a constant flow rate. A liquid is flowing through a reactor, liquid at constant flow rate. Right. A step input of tracer at a molar flow rate Ft naught 1 mole per minute is given to the reactor at time t equal to 0. The time variation of concentration C of the tracer at the exit of the reactor is as shown in the figure. T (1), 5, and here it is 1. So, this is C mole per liter. First question 8, the volumetric flow rate of the liquid through the reactor, so V naught. And question 9, the mean residence time of the fluid in the reactor, Tm. Right, these two we have to solve. So, you see that to answer the first question, we know Ft naught equal to V naught into Ct naught. Now, what is Ct naught? Ct naught is this, because we know that if I am giving a step tracer of step height C naught, this is the input, will lead to the output, say it is this sort, here this will be also equal to C naught, right. So, here it saturates to 1 mole per liter. So, Ct naught equal to 1, Ft naught equal to 1 mole per minute. So, V naught equal to 1 liter per minute. That is the answer. Next is Tm. So, this is a step input. So, F is equal to Ct divided by C naught, right. and df dt equal to E. So, what will be the E curve? E T, F curve will be just same as it is. This will saturating to 1, 1 and 5. So, up to 1 the slope is 0, right. From 1 to 5 the slope is, this is 4, this is 1, so 1 by 4. So, for E curve over 1 to 5 this, and again it is equal to 0. So, it is a kind of uniform distribution, and this is 1 and 5, the mean is 3, right. So, 3 seconds is the residence time, and V naught equal to 1 liter per minute. Okay. Then a liquid phase parallel reaction, liquid phase parallel reaction, A giving R and A giving S, right. So, RR is equal to K1 into Ca, and K1 is 0.3 second inverse. RS is equal to K2 only, 0 order reaction. K2 is also 0.3 kilomole per meter cube second. Is conducted in an isothermal PFR. So, it is conducted in a PFR. The inlet concentration of A, Ca naught, is 2 kilomole per meter cube, right. No product are present in the feed. Cr naught, Cs naught is 0. If the conversion of A is 80%, then the exit concentration of R is. So, XAF is 0.8. So, we have to calculate CRF. So, it is a PFR. So, you see the same thing basically. So, phi R by A is RR by minus RA, which is RR divided by RR plus RS, K1 CA plus C2. And this is equal to dCr by minus of dCA. So, which is K1 Ca by K1 Ca plus K2. So, CRF, this is Ca naught to CAF with a minus sign K1 Ca divided by K2 Ca, K1 Ca plus K2, right, dCA. Next, we have to do a bit of this algebra. K1, K1, K2, K2 cancels out. So, what it will give you? Yeah, this one. This Ca naught is 2, right, and CAF we have to calculate. CAF is how much? Ca naught into 1 minus XAF, Ca naught is 2 and XAF is 0.8, so 0.2, so this is 0.4. So, this is 0.4 and K1 and K2 they are numerically same, so they will cancel out. So, Ca divided by 1 plus Ca dCA, right. No, this is 2 to 0.4, correct, yeah. So, this is fast, it is 2 2.4, 1, Ca plus 1 minus 1, minus 1 divided by 1 plus Ca, dCa. So, it is minus of Ca plus ln 1 minus 1 plus Ca, right, 1 by x equal to ln x, integral ln x. So, it is minus ln of 1 plus Ca from 2 to 0.4. So, if I evaluate that, I will get the CRF. See, okay, no, let me skip that. Good questions. Okay, this is a very interesting problem. Also get problem 11. An isothermal CSTR volume 1 meter cube is used to carry out a first order liquid phase reaction, N equal to 1 liquid phase. Right, no change in volume basically. Liquid phase reaction, A giving product. Fresh feed at a volumetric flow rate Q entering the reactant. So, okay, let me draw the setup. Q is equal to 0.5 meter cube per minute and Ca naught equal to 1 mole per meter cube, and Q is equal to 0.5 meter cube per minute, and there is a recycle. Okay. So, what is stated? Fresh feed at a volumetric flow rate of Q containing reactant A at a concentration Ca naught mixes with a recycled stream at a volumetric flow rate Rq. So, this is R into Q, right, as shown in the figure. It is observed that when R is equal to 0.5, XAF is equal to 0.5. Now, if the recycle ratio is increased to 2, XAF is equal to what? So, obvious answer is we do not have to do anything, it is 0.5. Why? Because CSTR is a reactor where we have infinite recycle ratio, right, because from this V by Fa naught equal to R divided by R plus 1, sorry, R plus 1 into R divided by R plus 1 XAF to XAF dXA by minus RA. If I set R tending to infinity, we get V by Fa naught is equal to XA by minus RA, XAF to minus RA. So, it is MFR. So, if MFR is a reactor with internal infinite recycle ratio, if I am adding an external stream, there will be no change, external stream of recycling, then there will be no change in this conversion. So, conversion remains same. Okay.